Well guys, welcome back. I'm just playing a little game here written by Lux from the forums. So he whipped up this little shooter here. It's pretty fun actually. There's no, doesn't make much use of sprites or anything. It's mostly just primitive drawing. But it's pretty amazing what you can do with just some simple geometry. I like it a lot. I like this effect that he worked in it where you when the enemy dies, they leave little particles and you can gather them up and then release them for a nice attack there. That's pretty sweet. Good times all around. So yeah, I just wanted to show this off a little bit. And I want to show you one more thing. Check this out. Got me a new card. Oh yeah. GTX 670 baby. You feel free to be jealous right now. That's okay. I'll allow it. Unless you have like a 680, in which case you can go fuck right the hell off. But yeah, I wasn't planning on buying a new card, but my old one kind of exploded. The funny thing is, it still booted and it worked, but it wouldn't recognize the card, and the screen had like it was all fucked up. I could still kind of use my computer, but no graphics acceleration and 800 by 600 resolution. So yeah, spent a little money on this 670. The funny thing is, I don't even actually play that many games, but it'll really speed up my video encoding because that uses the GPU. So that's good for me. Doesn't really affect you guys. What else? I'm pretty sure there was something else I was gonna say or do, but I forgot. So today, what are we doing today? Well, I told you last time we're gonna do something called dynamic memory allocation, and we will do that. But first, we're gonna look at this picture. If I can open it, where's my preview? Picture viewer? Windows photo viewer. Yes. Look at this awesome picture. We're gonna put this picture as the background of our animated sprite demo. I'm gonna draw it in the background. So that seems simple enough. We'll just we'll load it as a sprite, even though it's a little inefficient to draw it as a sprite because there's no transparent pixels, so we wouldn't have to do the pixel test, but we'll draw it as a sprite anyways because we don't want to write a new function. So we go to game.h and we have to add a sprite. I cleaned my my whatchamacallit, my desktop, not on my computer, on my actual desk. So now I can see my keyboard. We want background sprite, and we want D3D color, background round, fuck me, surface. There. And it's going to be 800 by 600 because that's the size of our resolution. That is our resolution. Let's see if I can position my microphone here. It will allow me to look at my keyboard when I'm trying to find keys. Okay, now, so first we allocate or we declare these variables, and then we have to actually load them. So we go to game.cpp and we do what? We'll go here, load sprite, and background sprite, background surface, what else? Constant character pointer to file name, which will be, what did I call it? Badhaircut.bmp. Alright. We've got to move this into the folder. Like I said before, we're using the font thing, by the way, or whatever you called it. The continuation from lesson 21. This is lesson 22, by the way. Okay, so we put this in here. And, oh, I'm not putting this, fucker. I'm not putting this, bitmap on the website for download because it doesn't matter what you have as your background. So just make an 800 by 600 bitmap for your background. Let's see if I can get my properties going on here. And what is it? Details. So it's got to be 24 bits per pixel, 800 by 600 bitmap file. So just make one that satisfies those requirements, and then that's all you'll need. There's no point in me putting that up for download. Okay, so bad haircut.bmp. There. What's next? The width is, wait, 800, height is 600. The color key doesn't really matter, but D3D color XRGB. I'm gonna put the color key as what? 255 0 255. That's an ugly color, and I'm pretty sure it's not in that picture, so we don't want parts of the picture turning transparent. So we load the sprite, and that should be all I need to do. Now to draw the sprite, I have to draw it at the very beginning of the compose frame, right? Before I draw everything else, because everything else will be drawn on top of it. It's the background, so it has to be at the very back, which means we draw it first. So drawing it is simple. Draw graphics dot draw sprite 0 0 and background sprite, passing by address because that's how this function works. Okay, so let's build this mother and find all of our delicious errors. No errors, so let's run it. Let's see if this is gonna work. Of course nothing will go wrong. Nothing ever goes wrong. Never. Oh, something went wrong. Well, would you look at that. So whenever something goes wrong, what do? You move into release build first of all, and you start debugging. And here now we get some more information, and the information we get is unhandled exception in the framework Stack Overflow. So what the fuck is a Stack Overflow? Well, that is exactly what I was looking for, because it gives me a good excuse to explain some shit to you. But to do that, I'm going to have to get into a lot of theory here, so get ready for some bad diagrams and some incoherent explanations, because that's my business. Alright, so I think I've explained to you guys the stack before, but I'm going to go over it very quickly again. Hopefully very quickly. The stack is where it's one of the places where the memory for variables is allocated. Okay? So whenever we put a variable in a function, let's say I have a function and I say int x, and then I say float y, I don't know, whatever, dude. When the program's execution gets to this point, it allocates a space on the stack. So it's x, int and whatever the value is goes in here, right? Float y, whatever in here. By the way, don't message in don't put a comment saying that ints take 4 bytes and floats take 4 bytes and your addresses are all fucked up, because I know that. I'm just making it easy for explanation. I don't want to have to fill in 4 memory locations for every variable I put on my diagram, okay? So yes, ints take up 4 bytes in memory, but to simplify things, I'm going to say ints take up 1 address location, and so do floats, and everything else, just for argument's sake, okay? So that's how that works. And so let's say this is actually a code block. Let's say we got some if blah blah blah, then we create some variables, then we do some more shit, and then we leave our code block. When we leave the code block, oh, I just erased that mother. I didn't want to be drawing on my thing here. I wanted to draw on a different layer, but I forgot to change my frickin' layer. So yeah, when we leave this code block, this space on the stack becomes free again, and other variables can go here. So if I had an int blah over down here, then int blah would go in here, right? That's how the stack works. There's actually, you can't see it, but there is actually a pointer that points to the end of the stack. And so when we add a new variable, like we add int foo here, and then we give it some value, then this pointer is actually incremented down here, and it just keeps going. Now, what happens if we put something gigantic on the stack? We take a big steaming dump on that stack. We go int turd, and we dump, like, I don't know, an array of 10,000 ints onto the stack, right? No, that's not enough. That's not enough. We're going to put an array of 1 million. You can imagine me putting my pinky to my the corner of my mouth right now. 1 million ints. And we'll say 4 million. So what happens, of course, is that space all gets allocated in here. So all these addresses all the way down forever and ever, or at least for 4 million locations, get allocated, and the pointer gets moved all the way down here to 1 million. Address location 1 million. 1,042,042. Yeah, and that's a 4, because that's 4 million, by the way. Alright. The problem is that that actually doesn't happen, because the stack is limited in its size. I mean, there's obviously going to be an upper limit on your stack. You can't be more than the memory that's in your computer, right? But what's more is that the stack doesn't, like, the maximum size of your stack is not the amount of free memory in your computer. Your stack is only allocated a relatively small amount of space. And once that's filled, your program just basically explodes and dies. So, let me explain something to you. Let me do some splaining to you. 1 second. Alright, let's say that this little diagram here represents all the memory in your computer. Basically the RAM. Alright? These parts here is RAM that's currently being used by programs or by the operating system. So it's not free RAM. It's currently allocated to some other process. Now, when you start a program, when you execute an executable, what happens is the operating system will allocate a space in free memory for your program. So let's do that right now. We'll allocate a space in memory, and that this space is for our program. So what is all in this space here? Let's have a look-see. So in this space of memory, fuck you! I don't know why I get this thing that jumps over here that pisses me off every frickin' time. Okay, let's go like that. Yeah. I could have done this off screen too, but I'm gonna make you watch me fail at Photoshop. Okay, so in our memory for our program, what do we have? Well, we have some space here. Fuck you. We got some space here, and here is where our the actual program code will be loaded, the instructions for the program. There'll be space for the instructions. There's going to be some space allocated. Fucker. Space allocated for strings. Strings. Yes. And by strings, I mean string literals. So if you look at things like this, these strings here, they're actually sitting in memory somewhere, usually after the code, I think, after the instructions. And they're just in read-only memory. Not read-only memory, but you can't write to those string literal memory. It'll fuck your program up. So your strings are loaded in, your string literals, your string constants. Your code is loaded in, and here you'll have some space that will be allocated for your stack. And down here you might have some space for global variables. Alright? So you'll get some space in RAM, and your code is loaded in, your strings is loaded in. Your stack, there's nothing to do with that. Your globals might be initialized into here, to their initial values. And then the instruction pointer is pointed to the beginning of your program, and your program is started. And it runs, and it puts variables on the stack. Let's do this. Oh, this is this thing here. Yeah, you already knew that. All right. But if you if you declare something giant, you take a big steaming dump on the stack, it's not going to fit in here, and your program's going to crash. Now the stack is like, I think you can change the size when you're building your program, how big you want your stack to be, but it's usually about 1 megabyte or maybe 2. I'm not even sure really. I don't care. It's not a lot, all right, but it's plenty for what we usually need. But if you want to like put a whole giant frame buffer on your stack, it's not going to work. So how do we allocate gigantic arrays? Because obviously we should be able to allocate a giant array. Computers are used to working with gigantic amounts of data, right? Gigabytes. So we should be able to allocate an 800 by 600 surface. But if we don't do it on our stack, then where do we do it? Well, the answer is we allocate extra memory in these free areas. Here's the part of our program. But see, these non-shaded areas, they're all free RAM. And we can ask the operating system to give us some of this extra free RAM. We're not limited to what we can hold on our stack. The sky's the limit, or at least the amount of RAM in our computer. Or with virtual memory, I mean, you could get shit ton of big ass stuff, but it's not good. Anyways, so what we do is we call a function that will get us a block of RAM, and that function is called Malloc. It stands for memory allocation, and it returns a pointer it's a void pointer because it's not any specific type of data, like an int, a pointer to an int or anything, because you don't know. I mean, this function works for all kinds of memory allocation. So it returns a pointer without any data type, and you have to convert it to the type that you want to point to. So you tell it how many bytes here. I think it's like size t, but I'm going to say int bytes. So you say how many bytes you want, and it returns you a pointer to the allocated memory. So if I wanted to make my steaming pile, if I want to allocate a big steaming pile on the stack, I'd do something like this. I'd go, okay, int steaming pile. Actually, I'd go pointer to steaming pile. Int pointer p steaming pile is equal to Malloc 4,000,000. And that would work fine because I've got a buttload of RAM. Oh, by the way, I'd get an error for this because you have to convert it. You have to go int pointer here and convert this to a pointer to int. So I'd do this, and what would happen is when I call malloc with 4,000,000, the operating system will look around and it'll try to find a space in memory that has like a contiguous block of 4,000,000 bytes, or 4,000,000 ints, which is 16,000,000 bytes. Anyways, 16 megabytes, sort of, kind of, and it'll find a good space of memory. It'll say, oh, you can fit that in here easy, and it will allocate us up. Fucker. Maybe it'll stick it right in here. So it'll allocate us up our 16 megabytes, and it'll return a pointer. So now steaming pile is pointing to the beginning of this block of data, this memory block. And now we can access all this memory and do with it as we please. We can go p steaming pile. I should have made the name shorter. At 400,000 is equal to 69. Yeah. Or we could do whatever the hell we want, because that's our memory now. One thing though, one difference between stack allocation and dynamic allocation is if you allocate on the stack, right? If you go int blah, so you've got a code block in here, you go int blah, and you get yourself a nice int blah on the stack. When you're done with that int, when you leave this code block, the stack pointer will be decremented, and this will be basically returned or freed from the stack, and that space will be able to be used by other variables. But once you call malloc and you allocate memory, that memory is basically tied up permanently. Nothing else can use that, and that will stay. If you leave a function, if you leave the code block, this memory will stay allocated. And if you're finished with this memory, then it's just being done. It's wasted space basically. And if your program, if it calls a function, and if every time that function runs, it allocates memory, eventually you're going to fill up all your memory, and your computer's going to crash. That's called a memory leak, and it actually happened quite often in Windows 98 when I used to run it. But anyways, it's not good times. But there is a way that we can get out of this this vicious cycle, and that is another function called free. What free does is it tells the operating system, okay, we don't need this memory anymore. You can Oh, that wasn't good. It tells the operating system, okay, I don't want this shit anymore, you can have it back. And you have to pass it the pointer to the beginning of the block that you allocated with Malloc. So you'd call free and you'd pass it point p steaming pile. I think I said you could pass it, but whatever. Steaming pile. Pass it steaming pile, and what'll happen is this memory here will be deallocated. It'll be freed, and so now some other program or our program can use it. So you call Malloc to get a block of memory, and you call free to return that block to the operating system. They come in pairs. For every Malloc that you call in your program, you should have a corresponding free somewhere else in the program. But it doesn't have to be in the same function or anything. That's the beauty. That's one of the beauties of dynamic memory allocation. If you write a function, like let's say, I don't know, void myfunc, and you create some variables on the stack, when that function leaves, those variables will always die. They will never remain. So if you create some object inside of your function, that object will be destroyed at the end of your function. But if you allocate the object with Malloc, you can have objects that live beyond the end of a function, and they can persist, and that is useful sometimes. But it's also more responsibility, because you have to make sure that you free that at some future date when you are no longer needing its services. So, I'm going to pause the video and think. Alright, let's go over the advantages of dynamic memory allocation. So the two advantages I've already told you of are, number one, it gives us access to a lot more space, right? We got all this free memory that we can use, whereas stack allocation only gives us this little slice in here. So that's number one. That's a big one. Number two is that the memory that's allocated. Wait, I think I just added an E onto the end of that. The memory that's allocated by Malloc is persistent. That's what this word actually says, persistent. What that means is it doesn't die at the end of a code block, like variables that are declared on the stack. At the end of the code block, they all die a horrible, horrible death. But the Malloc memory is basically immortal. It stays alive until you free it. There can be only one. And the last advantage of dynamic memory allocation is that it is dynamic. What do I mean by that? Well, memory allocation, or the allocation of variables and arrays on the stack, is static. What do I mean by static? Well, to understand that, you have to understand how the compiler actually accesses variables on the stack. And what it does is it has something called a stack pointer, and it remembers where all our variables are relative to the stack pointer. So if we have a function that has like int a, int b, int c, and then it has some stuff down here, and then it has like a plus b, c is equal to a plus b, or something like that. Well, when the program gets down here, it allocates a, b, and c, and we'll say the stack pointer points to the last allocated variable. This is sp, and these are all ints, so I'll draw them as ints. and some values in here, right? So what does the how does the code actually look like when you're accessing these variables? Well, what it is it's SP. When you access C, you're actually accessing SP, the stack pointer. And so what this is saying is SP is equal to SP minus 2. Get rid of this here. And I gotta add extra brackets here. Plus SP minus 1. So all this is relative to the stack pointer. Now what does this mean? Well, what it means is the compiler has to know where every single variable, well, within a code block or within a frame, it has to know where every single variable is going to be ahead of time. So if you have, so you got int a, b, c, and then you've got an array here, and it takes up, let's say, int array, and it takes up 1, 2, 3, 4, 5. And then down here you've got an int x here, and this is where stack pointer is pointing. Alright, how to explain this? So if we wanted to access A now, what would A be? A would be stack pointer minus 1, 2, 3, 4, 5, 6, 7, 8. Minus 8. That's how you would be accessing A. So when you write A, the compiler thinks stack pointer minus 8. The reason it can make that calculation is because somewhere in our code we did something like this. Int ARR. And that's 5. So we allocated an array of size 5. So we know basically we know how many bytes are between our stack pointer and where A is. But what if we allocated our array using some variable x, which depends on user input or some other thing? This variable can change depending on how the program is run, or when it's run, or with what input it's run. And depending on x, the size of this array changes. So the distance from SP to A will also change. And therefore we cannot predict where A is going to be relative to SP, because SP's position depends on this, and this depends on the value of x. So basically, you are not allowed to have dynamically sized arrays on the stack, because that would fuck up SP's position. You couldn't predict where SP is going to be, so then you couldn't predict where your variables will be relative to SP. You couldn't access any of your variables on the stack because you wouldn't know where they are. You have to know at compile time where everything is going to be on the stack. And that is why you're not allowed to use variables when you declare arrays. You can't declare it with a variable. You have to declare it with a constant. With a literal constant or with a constant variable. You can't have it with a variable that can change. So, stacks are static. That's what I'm trying to tell you. They're stuck in their ways. But we don't have that problem with Malloc, because Malloc doesn't depend on a stack pointer reference to determine where its variables are. What happens is when you call malloc, you get an address, and that's stored in the pointer, and then the pointer tells you where the pointer remembers where that thing is in the memory, and the pointer never moves. There's no relativism. There's no referencing, so you don't have to worry about keeping things static. when you use dynamic memory allocation. So that's why you can do Malloc X, no problem. That works fine. And what that means is that you can tailor the amount of memory that you allocate. You can tailor it to the situation at hand. Whereas with static, you have to know ahead of time how much memory space you need. All right. Imagine you have a game and you've got a bunch of sprites. Some sprites are small and some sprites are large. But you only have one type of sprite, what would I call it? Sprite structure. And inside that structure, you have an array. If you are declaring this stuff on the stack, you have to make that array big enough to hold the largest sprite surface. And for all your sprites that are smaller than that, you're going to have wasted space. Right? That's if you declare the surface inside of the structure. But if you had dynamic memory allocation, you would have a pointer to the surface inside of your structure here, and you would just dynamically allocate surface memory blocks to serve the size that you need for that particular sprite. Don't worry if that last explanation didn't make any sense, because I'm going to be showing you in code later on. But basically, the third advantage of using dynamic memory allocation is that you can choose the size of the memory block that you want at runtime. You don't have to know it ahead of time. And like I said before, they don't die, they're persistent, and they allow us to allocate much more space than with the stack. So, that is the difference between stack allocation and dynamic memory allocation, or heap. Oh, by the way, all of this free memory here, this is all collectively referred to as the heap, okay? Or sometimes the free store, but usually it's called the heap. And that's what I'm going to call it. If I call it something like that, I'll call it the heap. So that's heap allocation versus stack allocation. The other kind of allocation is global allocation, but we're not going to be talking about that until maybe later, because we don't use it really, and it's evil. So you shouldn't use it. But yeah, that's the difference between stack and heap. And we call Malloc and free to do that stuff. And now I'm going to show you how to do it. So let's go back to our thing here. I'm just going to get a... Okay, so in order to load this background dynamically, I'm going to have to change my load sprite function. Now, actually, it shouldn't be too hard because of the way I've set it up. Right. The sprite structure, it doesn't contain, it doesn't actually hold the the array inside of the structure. I could put the array directly in the structure. I could go surface, and I don't know, I could do something like 80 by 60 or something like that. And I could put it directly in the structure. And if I did that, if I put the surface inside the structure, it would have an advantage. And that advantage would be the... Wait, I gotta find what... Here, this is what I want. If the structure, if the surface was inside the structure, then I wouldn't have to do stuff like allocate a sprite, the object here, and then allocate the surface after it, because the surface would be inside the sprite structure. I'd only need one line, which is better. But can you think of why I didn't do it like that? Why did I make it so that you have to allocate the surface separately. And then when you do the create sprite, you pass the pointer to the surface. The reason why I did it separately is because if you put it inside here, you have to specify its size, right? Because we're all, up until now, we've only done static memory allocation. So we had to know the size of our array ahead of time. And if you do this, you're stuck with only one size of sprite, right? So if I do 80 by 60, then if I wanted a 100 by 100 sprite, I'd be fucked, right? And if I wanted a 50 by 50 sprite, I'd be wasting space. So that's why I made this thing a pointer to a surface. Then I could allocate my surfaces separately outside of the sprite object, and I would have the freedom to have different sizes of surfaces. But with that freedom came the problem of having my sprite split into two different allocations. One allocation was for the surface and one was for the sprite. It wasn't nice and integrated. But now we can make it integrated because we don't need that external surface. So we leave it like it was, which is a pointer to surface. But now we do something a little different here. In our load surface function, we're not going to pass it a pointer to the surface because we're going to allocate that surface on the heap. So we don't need to pass it a pointer to an external array, which is a surface. Alright, so we do load sprite here. We get rid of that pointer to surface. Now, down here we gotta find our load sprite. Here it is, load sprite. So we load bitmap, but instead of using the surface pointer that was passed to the function, we use the pointer that is part of the object. So we say load the bitmap onto whatever is pointed to by this sprite surface pointer. But to do that, first we have to make that pointer point to a valid buffer. So we call Malloc. We go sprite pointer to surface is equal to, and then we go d3d color pointer because we have to cast the void pointer to a specific type. We go Malloc. We say, hey operating system, give us some memory. Malloc is in, I think it's in std include stdlib. There. Malloc is in the standard library. And there we go. Now we need to tell it the size of the block in bytes. So we go size of d3d color. We want the size of one d3d color pixel times, I'll just do 800 by 600 because that's the size of our, wait, no, that would be stupid. Don't do what I would do. We use the width and height that was passed to the function, obviously. You laugh, but it's hard to talk and do stuff at the same time. It's like walking and chewing bubblegum. That shit's hard, yo. Okay, and there we go. So we get the size of d3d color, which is 4. There's 4 bytes for every pixel, times our width, times our height. And that's the size of the surface that we want to allocate. We call Malloc with that size. The operating system finds a block of memory that size, and it says, okay, this memory is now off limits, and it passes us a pointer to the beginning of that block. And now that our pointer is pointing to the beginning of a valid block of memory, we use that pointer with load bitmap to load the image onto that block of memory, onto that surface. And then we have our dynamically allocated hoo-ha. But we're not quite finished. Like I said before, whenever you load Whenever you load something, or whenever you allocate memory dynamically, you have to deallocate it when you're finished. So we go back to this thing here, and we go void free sprite and sprite pointer to sprite. That's all we need. And let's go back down here. So void free sprite. Why is that not giving me something? Grr. Burpee. Free sprite. Well, I don't see the problem. This should work fine. Sprite pointer. No, wait. Dude. Sprite pointer. Sprite. And freeing is very simple. We just go sprite surface. I don't have to put the sprite in there, but I did it anyways. No, I do have to put it. Never mind. This is an object. Don't worry, I'm talking bullshit here. Free. And we just pass it the pointer. And that's that. Now I could do some other stuff. I could initialize it, the pointer to null, and then here I could check to see if the pointer is null or not. But fuck it. You know what? We're gonna live dangerously. I'll probably do it a little more nicer, more nice. I don't know. I'll do it better later on when we're serious about it. But for now, this is fine. This is the bare minimum of what you need. So we call load sprite to load our sprite, and we call free sprite when we're finished with it. All right. So let's look at stuff. Actually, to begin with, we're not going to free the sprite, because I don't want to explain too much stuff before we get moving on. So we're going to work with just load sprite, and we're not going to free it when we're finished. It's okay when your program actually finally exits. Windows does free up all the memory that was allocated to it, so it's not like that memory is lost forever and ever. But generally, you always want to free when you load or when you allocate. Okay, we got failure, error, load sprite does not take 6 arguments. That is correct. Does not take this argument here. Background surface. And there'll be one more here. We don't have to pass this nasty pointer in either. And now we succeeded. So let's see if this works. It didn't work. Damn it! Okay. This one I wasn't really sure about, but I figured something might not work properly. Oh, I know why it didn't work. Yeah, duh. Break. Can you think of why it didn't work? Last chance before I give you the answer. It's because although we made the memory allocation, we made it dynamic, but we still have this big turd that's sitting in our stack, and it's not helping. So let's get rid of it, and let's see if we can live dangerously. There you go. There's our background. See if I can run it in release. There you go. So that works fine. There's no problem with that. I'm going to reduce the number of sprites. Now, because we're drawing a background, it takes more time. Drop it down to 400. See how that runs. That runs better. Alright, so that's our background. But we're not finished yet, because we're not freeing the memory that we allocated, and we must free it. It is our responsibility. So first thing, we don't need this anymore because we're not using it. Now we just have, let me just do this. Control X, Control V, Enter, delete. There we go. So now we just have one sprite. We just have to declare a single sprite object here, and that's all we need. This one thing covers the whole sprite, and this array of sprites covers all those sprites. And we need the animated sprite template to hold the whole thing together. Now, animated sprite instance dudes. That's fine. Okay, what did I want to do again? I wanted to get that freeing working. The problem with free sprite is, well, it's easy for let me just get back to game.cpp. For this load sprite, here we directly load the sprite. So if we want to free it, we have to call free sprite. But where do we call it? We want to call free sprite basically at the end of the program when the game object is destroyed. Then we want to free our sprites. This is the constructor. So this gets called, all this stuff gets called when the game object is born. And we want to free it when the game object dies. Now this isn't a C topic, this is a C++ thing. But I'm going to show you guys anyways because we're very close to starting our C++ adventure. Up until now it's just been basic straight C, but so this thing here, this function, is the constructor. When you declare a constructor, you just give the name of the class. This is the class name, game, and then the parameters. But there's also another kind of special member function called a Destructor, and it's called when the object dies. And you declare it by going tilde and then the name of the class. So tilde game, and it never takes any parameters, so this has to be empty. This is the Destructor. So now we go to game .cpp and I forget now. Just game tilde game, and there's our destructor. Now in here we want to do all of the code that we call when the game object dies. Up until now we haven't had to call anything because everything's been on the stack, and so when the object dies it's all automatically cleaned up. But in this case we need to do stuff, so we call free sprite and background sprite, and that will free our background sprite when we are finished with it. Failed. Dude surfaces undeclared identifier. Ah, right, because load animated sprite is different. See, that's the thing, we don't need the surfaces for load animated sprite anymore, so we can get rid of them there. And then we gotta go here and we go load animated sprite, and surfaces no longer necessary because we're allocating them dynamically within the load sprite function. And then we have to go back down here and we go here, and we go, where's load animated sprite? And we delete it from here as well. And that should clear up that problem. Problem solved. Now let's see if this free sprite actually works properly. So no problem for starting, and when we finish we didn't get any errors, so that's fine. But that is only covering our background. What about our sprites that were loaded with load animated sprite? In order to free them, we have to create a counterpart function called free animated sprite. So let's do that right now. There's a lot of symmetry involved with dynamic memory allocation. So for every function that you have that allocates something, you should have a counterpart that frees it. Free animated sprite. And we do animated sprite template pointer to. I don't like that name. I don't like that name whatsoever, but whatever. Whatever, bro. Okay, now. Where are we at? Load animated sprite. Free animated sprite. So, all we gotta do is we gotta undo what was done up in load. So what was up in load? Well, we loaded sprites from 0 to n frames. So here, I'll just copy this. Copy. Paste. Index equals 0 as long as index is less than templat pointer to... what? I'm way ahead of you. Booyah. How you like that? Okay. Templat pointer to n frames. So we loop through all of the frames of the animated sprite template, and for each frame we go templat pointer to frames, not sprites, frames. Right? Because frames is an array of sprites. And we pass that address to free sprite. Don't forget to change that. And now we're freeing every single sprite frame that is managed by our animated sprite template. Alright, so that should work fine. Yeah, that should work fine. Build. Okay, no errors. Loaded fine and freed fine. No problem. Except that we haven't actually called the function yet, so that didn't do anything. Okay, so here, same thing. We call load animated sprite in the constructor. So we call free animated sprite in the Destructor. And it's dude template, so pass it a pointer to the dude template. Build. Go. End. And we didn't crash, so let's assume that it worked fine. That's what I'm going to assume. Yeah, so that's how that works. You just do the opposite of what you did in load. So in load, we called load sprite inside of a loop. So in free, we call free sprite inside of a loop. In load sprite, we called Malloc. So in free sprite, we call free. And now we are becoming responsible members of society because we're freeing up our memory. Now there is one more thing that there's a couple of things I can still do in here. I'm going to do one of them right now. And that one thing is we still got a kind of situation like we had before, because we have animated sprite template, but then outside of that we have an array of sprites. So what I'm going to do is I'm going to integrate this array of sprites into the animated sprite template. How will I do that? Watch and learn. We go to animated sprite template. So load animated sprite. We're not going to pass it a pointer to an array of sprites. Not going to happen. Now we go game.cpp. Where's load animated sprite? Here it is. Not passing you that. You cannot have my pointer. No pointer for you. Instead, we're going to allocate that dynamically. So here we go. What do? We go templat pointer to frames is equal to sprite pointer to malloc. Damn it, I need to Well, I got stdlib in here. What the fuck, bro? Where's my fucking IntelliSense? I want my IntelliSense. God damn it. I know there's definitely going to be something wrong. Fuck it, I don't need IntelliSense. I know what I'm doing. It always pisses me off when it's not working, because I know that means something's fucked up somewhere. Whatever. Whatever, bro. Size of sprite, right? Times how many sprites we want. That's n frames. We want n frames number of sprites. Right? So here we allocate our sprite array. And now we have, instead of sprites here, we just use our template pointer, which has been set to point to a block of memory of the correct size. And so now we're going to load our sprites into this block here, which was allocated dynamically. And because it was allocated dynamically, we have to go into free sprites, free animated sprite. And we want to free the, here we free individual sprites, but at the end we want to free the whole array of sprite memory. So when we call free sprite, that's basically freeing the what do you call it? Freeing the surface that's associated with a sprite. But now we have to call free, just a naked free call, to free the array of sprite objects. So what do we have here? So we just, template pointed to frames. Yes. We free that. Right? Because it was allocated up here, so it has to be freed down here. For every malloc, you have a free. And you have to remember, you have to allocate your array of sprites before you actually load the surfaces onto them. And here you have to free the surfaces before you free the sprites themselves. If you free the sprites first, then these frames are all going to be garbage data and you're going to fuck everything up, right? You can't start accessing data once you've freed it. You can't access a memory location once you've freed it, because now when you free it, you're telling the operating system, I don't need this anymore. And then you go back and you're like, well, wait a minute, I just want one more thing here. No, you can't do that. It's like moving out of your apartment and then coming back like 2 months later and, you know, just saying, oh, I think I forgot a jar of olives in my refrigerator there. Let me just have my olives. No, you can't have your olives. You should have thought of that before you moved out. Okay, so remember, the order in which you allocate things and free things is very important. Don't fuck up the order. The order should be symmetrical. If you allocated first, you should free it last. Alright? So now I've freed this up. And I failed. Sprites undeclared identifier. Right, because we don't need that anymore. I don't need your stinking sprites, because I'm loading my shit up with Malloc, bro. Failed. Function does not take 8 arguments. That's correct. It does not take 8 arguments, because we don't need your stupid statically allocated array. Static arrays suck balls. We're all dynamic up in this shit. Okay, now that I did that, that means I don't need this anymore. So I can live now with just one single object here declared. One single animated sprite template object will serve to load my whole shit. And then, of course, I need separate instances, but we want the instances to be separate, obviously. That much is obvious, I hope. Build. Now I could also make it so that this thing is also loaded dynamically, but I won't go that far. Let's run. Make sure I haven't fucked anything up. Okay, so it's working fine. And it's all dynamic now. It's like, this works too? Good. Good times. So that is dynamic memory allocation. Oh god, look at all this mess. All gone. Ha ha ha. Okay, so basically, I don't like this stack. This stack sucks. Wait a second. Alright, so basically this is what we had before, right? We had a animated sprite template. That's what this is. Animated sprite template object on the stack inside of our game object, so it's on the stack. Let me just show you something quickly. Wait, let me see here. If we go to what does that look? What was I going to show you? We go to windows.cpp. We see that our game object is created. Here's the win main, which is a lot like the main in a console application, and it does some stuff. And here, the game object is created, and you can see it's created just on the stack because there's no malloc or anything else like that. Just the name of the type and then the type. And these are the parameters that get passed to the constructor. So this is created on the stack. So that means that all the variables inside of it also go on the stack. So here is part of our, we'll say that this is part of our game object on the stack. Inside of our game object, which is on the stack, we have all of these variables declared. So we have the active or the animated sprite template on the stack. And we have our array of sprite objects on the stack. And then we have our array of surfaces, which is complicated because it was like an array of arrays of D3D colors. It's just a big thing of D3D colors and a big array of D3D colors, and we divided it logically into sections. And each of those sections represented one surface, right? So we had the pointer to frames in the sprite template. We caused that to point to the first, what do you call it? The beginning of the array of sprites, right? The array of sprite objects. And every surface pointer in the array of sprites, every sprite object in that array had a surface pointer. And those surface pointers were made to point to locations inside of our surface array, which correspond to the separate surfaces for the separate frames. And that is the situation we had before. Now what we have, let me just get rid of all this. No, I got rid of too much. I don't want to get rid of all of that. Wait a second. Alright, so the situation now is we still have our animated sprite template on the stack, but instead of this pointing to another thing on the stack, what happens is we call Malloc, and this now will point to an array of sprite, an array of sprite objects. These are sprites. Right? So let's say we have 4 frames of animation. And each one of these will now point to a separate and independent array of D3D color types. And this array of D3D colors is the surface. So now each one of these ones points to separate surfaces in memory, all allocated in the heap with Malloc. So when we create the animated sprite template First, it creates this array of sprite objects, and then for every sprite, it loads a separate surface in the heap. And when we free the animated sprite template, first it frees each of these surfaces, it frees these up, gets rid of them, and finally, when these are all freed, then it frees the array of sprites. Alright? That's how the loading and the freeing works. And it works really nice. It's good stuff. And it makes me so happy. Why am I happy? Because it's, look at this, it's much nicer. We just have this one thing takes care of all that shit. Oh, it's good times. And this is the Destructor, very important. Now, that's the end of this lesson, but you do not touch that dial because I have a very important announcement to make. First thing I want to say is basically this is pretty much the end of all the stuff I wanted to teach you guys about just straight C, just straight structured programming in C. So from now on, well, not from now on, but in the future, we are going to be very soon moving into C++. We're going to be creating our own classes. We're going to be using all that good stuff, polymorphism and abstraction and data access and inheritance, all that happy crappy, which will make our programs a lot more sexier, a lot more sex appeal in our code. It won't make them faster, but it should make them more manageable, more maintainable, and more bug-proof. So that's what we're moving into. But now I have a little thing that I want to discuss with you guys, and that little thing is the future. Just a little thing known as the future, all the way to the year 2000. Where we are going to be talking, well, I don't know what we're going to be talking about yet because I haven't discussed it with you. Now I'm rambling. I gotta stop rambling. What I mean to say is we have reached a fork in the road. We can take one path or we can take another path. Now the path that I've been planning on taking for the longest time was, once we've finished all the stuff I wanted to teach about structured programming, we make a fairly, I wouldn't say ambitious, but more ambitious than anything we've done up until now. A game that is more ambitious than anything we've done up until now. It'll probably span a few episodes, so it'll maybe take, in total, maybe 3 or 4 or even 5 hours to complete. The game I was thinking of was a kind of platformer game, maybe with shooting, with animated sprites that run, and enemies and levels and shit like that. So a more game-like game than we have done yet, and doing it all in structured programming, basically just to wrap up everything we've done so far into one neat package and show you what you can do with this shit. Not so much introducing many new topics, although I'm sure we'll come across a bunch of new things, but definitely showing you some techniques on how to use these programming constructs. Techniques like how to implement scrolling in a game or something like that. So not teaching any new language topics, but teaching new things about how to implement game worlds in code, I guess. So that was my plan. But now I'm thinking maybe we should just go directly starting into C++. My plan was to do the game and then move into C++. And I would call this stuff, I would call this the intermediate lesson series. And the stuff that came before it, this would have been the beginner series, right? I hope beginner has 2 N's because I'm not sure. Alright. The other plan we can do is we can skip the game. We can jump directly into C++. Now, what benefits does this have? Well, if you want to jump right into C++, this will get you there faster. We won't have to spend time making this game, which will take a bit of time. And I know a lot of you are interested in learning how I made the framework, basically the guts of the framework. And I will teach that after teaching a little bit of the C++ stuff. So after I teach the basics of classes, then we're going to learn the framework, and then we're going to learn more C++ stuff. So if you skip the game here, you'll get to the framework faster, and you'll get to the C++ stuff faster. And what we can do is maybe after this point, or after this point, or after this point, then we can make the game. But we'll make the game in C++. This is game in C++. This is game in structured C. All right. So we're still going to make the game, but it might be better to make the game in C++ because our ultimate goal is programming in C++. So from one perspective, it can be a waste. It can be seen as a waste of time to spend all that time making a game in structured C when we really don't want to learn how to make games in structured C. It's not a good idea to make a game in structured C. So this is not a bad idea. It's still good to learn how to do this stuff, and it's still excellent practice. But it might be even better use of your time to learn that same thing in C++. So my plan was to do one final wrap-up in C and then move to C++. But we can skip to C++, which will get us to the framework faster and will allow us to make our ambitious game in C++. So it'll give us an accelerated practice of the actual object-oriented programming paradigm. So that's our choice. Now what I want you guys to do is I want you guys to go to the forum and I want you to vote on what you want me to do next. I'm going to make a poll, and you can answer the poll, obviously, and you guys will decide whether I make the game first or whether I just jump into C++ and make the game later on. I might make it after teaching the basics of C++. I might make it after teaching the framework. I'm not sure yet, but in any case, those are the two choices that lie before you. So I want you guys to go to the forum and vote. Vote for your choice of what you want to do in the future. My original plan was to make the game in structured C, and that's kind of what I'm leaning towards right now. But if I get enough response of people who want to jump directly into C and make the game later, if there are enough of you who really want that, then I'm open to that. So either way, let me know what you are interested in, and that is what we will do. Let it not be said that the Chile does not believe in democracy. Now, if you are interested in homework, what you can do is you can go here. You see that we've converted our animated sprite template and our sprite object here. We've converted these to using dynamic memory, but our font system here still uses static memory. We still have to have a separate array on the stack for our surface array, and that's not good. So for homework, if you want, it's not a big deal, but if you want to practice this shit, why don't you try converting the font functions to using dynamic memory allocation. So you'll need to change the load font, and you'll need to add a free font function. So you can do that dynamically, or you can do other stuff, but you should do something, because just watching will not allow you to learn this shit. I guarantee. So now my throat is dry and I am thirsty. and kind of tired. So that's a good time to stop this freaking video. And I will see you guys later. Don't forget to vote for what you want to do in the future, because it's important. The future of the Chili series rests in your hands.